Welcome to Analog Microelectronic Circuits class. This is Unit 3, Lecture number 2. And in today's class, we'll look at the frequency response of CS amplifier. So in yesterday's class, we have seen the high frequency equivalent circuit of MOSFET. We included the structural capacitance and the depletion layer capacitance, and we made a simplified circuit by just ignoring the structural capacitance. And we defined a performance metric called unity gain frequency. That is a frequency at which the magnitude of short circuit current gain of a CS configuration becomes unity, right? So that we derived, and we now we have the formula, or now we have the equation for unity gain frequency. It is Gm by 2 pi into CGS plus CGD, right? So with that, with the understanding of high frequency equivalent circuit and unity gain frequency, let us move to the next important section, which is frequency response of an amplifier. So whatever we are doing now in the first 3 lectures will be repeated for BJT also. Uh, all right, so we'll look at the frequency response of CS amplifier. Now let me ask this question first. What do you understand by the term frequency response? You can give your responses in the chat box. What do you understand by the term frequency response? For the explanation of this, let me take an example. Meanwhile, you can post your answers in the chat box. Yeah, I'll look at your responses. Let me just draw the circuit. So I have taken a MOSFET. I have given voltage divider biasing, and to the input side, I'm giving the signal through a source. Source is having some resistance. That is what I have marked here as this resistance. I call it as R signal. This is one coupling capacitor. We call it as CC1. This is R1, R2. This is RD and RS. This is another capacitor here. We call this as CS. And this is another capacitor CC2 here, which will, from this point we'll take output, and this is CC2. All right. Yeah, so there are some responses. Variation with respect to frequency. Yes, variation of what? Yeah, variation of gain of the circuit with respect to frequency. Frequency versus gain, output dependent on frequency. The way in which the amplifier gain varies with the frequency of input signal. Yes, change in output due to frequency. Yes, so all the responses are almost correct. So now my question is, this is not a this circuit is familiar to you, right? Whatever you are seeing on the screen is a familiar circuit. And if you remember, can you tell me the voltage gain expression for this circuit, AV? Okay, let me check with someone. Abhirami, are you there? Abhirami?
Yes, sir.
Yeah, Abhirami, can you tell me what will be the voltage gain?
Minus GM into RC parallel R0.
Where is RC in this?
No, sorry, RD parallel RL.
RD parallel
RL.
R L.
RL.
RD parallel RL. Okay. Or
Parallel
yeah, yeah, R naught is also there. Yes, very good. So this is a gain expression. Now the question, so those who responded here, that the frequency response of an amplifier is the variation of gain with respect to frequency. Now, by looking at the gain expression, how can we say that there will be some variation with respect to frequency? So now the gain expression is available here, minus GM into RD parallel RL parallel R naught. And now by looking at this gain expression, we cannot see any frequency sensitive elements, right? Are there any frequency sensitive elements?
So capacitor.
No, but in this expression it is not there, right?
Yeah,
I'm
yeah, not
asking,
in.
yeah, there are no frequency sensitive elements in this gain expression. Oh, GM is not depending on frequency, Kartikeya.
Sir, in the expression that we did yesterday, FT.
Oh, that is unity gain frequency. Your unity gain frequency depends on GM, but what is GM? What decides GM? This, right? There is no frequency term in this. Or if you write in any form, there is no frequency term. Yeah, but your unity gain frequency is determined by GM. That is true. But that doesn't mean that GM is depending on frequency. Is that clear, Kartikeya?
Yes, sir. Yes, sir.
Yeah. All right. So the gain what we have written here is called as mid-frequency gain. And in mid-frequency gain, the capacitors are not considered. If you remember, I told you that the capacitors were acting as short, right? So since capacitors were acting as short, we did not include those capacitors in the gain expression, or the gain expression what we have right here is independent of frequency because we did not consider any frequency sensitive elements, right? But we know that, or at least from your basic electronics classes, you would have heard and you would have seen this graph, frequency response graph, where we'll vary frequency of the input signal, and we'll plot V naught by V in, which is nothing but gain, the magnitude of V naught by V in. We'll plot in decibels here. And if you remember, you would have seen a graph where the gain will be constant in the mid frequency range, and you would have seen that the gain will be dropping towards the lower frequency, gain will be dropping towards higher frequency also. I don't know how many of you remember this graph. Probably you would have seen this graph for your common emitter amplifier, not for a common source amplifier, but the same thing holds good even here. And if you have seen this kind of graph in your first semester, you can you can respond in the chat box. I'll be explaining how, what all these things are. Now, in the frequency response, again, you would have marked something called as lower cutoff frequency. You may call it as FL, higher cutoff frequency, you may call it as FH. And from this, you would have definitely defined something called as bandwidth. Whether, have you seen this frequency response graph? All right. So yeah, as a part of your first semester, you have seen, especially you have seen for a common emitter amplifier. Now, so why I have taken this graph first itself is, I want to say that the gain what we have written here, the gain expression what we have written here, which is AV equals minus GM into RD parallel RL parallel R naught, where there are no frequency sensitive elements, represents this area or this portion, right? And this portion is often called as this is called as mid-frequency band, where we are not considering the effect of any capacitors. Now, as we have understood the high frequency equivalent circuit of MOSFET, let me bring in the high frequency capacitors also. So okay, let me check with one of you. All right, Charan, are you there?
Yes, sir.
Yeah, Charan, can you tell me what are the high frequency capacitors I need to include in this circuit? You can see the MOSFET, right?
Yes, sir.
Yeah, which are the capacitors I need to include?
CS,
Okay, CSN.
I think only CS.
All right, my question is, which are the high frequency, from the high frequency equivalent circuit, which all capacitors I can include in the circuit? Are you responding to my question? I'm not able to hear.
No, sir, I don't know.
All right, no problem, no problem. Yeah. So what I'm asking is, in the circuit diagram, which all capacitors you need to include. Now, look at yesterday's equivalent circuit. So here we know that we have included CGD and CGS. So both of those capacitors can be included here. How to include? You will have your CGS between your the gate and the source terminal, which is CGS. You will have the capacitor CGS. Now this is marked as CGS. Similarly, between the gate and drain, you have other capacitor, which is CGD. All right. So you have CGS and CGD, and these are the high frequency capacitors what I need to include here. Now let me tell you one thing. Why have I? Why haven't? Yeah. So now the reason of including all the capacitors here is just to study the frequency response. So you are clear that in the mid frequency band we did not consider any capacitor. I'll answer or I'll explain why we did not consider, or why, how can we neglect the capacitors in the mid frequency band very shortly. Now if you look at the circuit diagram and if you look at the frequency response, you can see that there is a fall here. At low frequency there is a fall, and at high frequency there is a fall. Right. Now okay, let me explain one by one. First, let me explain about this mid frequency range, because I had questions from that even before. So mid frequency is nothing but so by calling it as mid frequency, we are what we meant is this is actually the signal frequency or the frequency of interest. Right. Now, if you look at the circuit diagram, you have different capacitors. How many capacitors do you have? You have three coupling capacitors, which are marked in red, and two capacitors, which are the high frequency capacitors, which are marked in blue. So let me consider both here. The first one is CC1, CC2, and CS. We call these as coupling and bypass capacitors. Now, the second set is we have CGS and CGD, which are the high frequency capacitors or the parasitic or structural capacitors. Right. Now, I'll take some sample values and I'll show how these capacitors will not have any effect. Right. Now, in order to understand about the effect or the reactance offered by the capacitance, we know that the reactance offered by any capacitor is Xc is equal to 1 by 2 pi f into C. Right. So give me a quick answer for this. Say I am considering, so when I say mid frequency, I am looking for actually a frequency of say some 1 megahertz, and say I have CC1 value around 10 microfarad. This is the capacitor value I have. Now, can you tell me what is the Xc value, or if I write the capacitor CC1, what is the reactance of this XCC1 at 1 megahertz with a capacitance value of 10 microfarad? Can one of you calculate and tell me what is the value here? Yeah, it is that it is reactance, right? Yeah, it is 0.0159. Yeah, it is very small, 0.0159. I think you also will agree with me that, yeah, I got it, Makam, no issues. So you also will agree with this, that this reactance is very, very low, right? So if it is very, very low, that means I can actually neglect it, or how I'll neglect it, I'll consider the reactance to be 0, or this will result in me assuming that these capacitors are acting as short. Right. So let me mark it in red here. These capacitors here, these capacitors are acting as short. The reason is this: at the signal frequency, the typical values what we take for these capacitors will give you a very low value that result in a short. That is why there is no role for these capacitors in mid frequency. Or now you can actually appreciate the fact that Why I am telling that this resistance will be bypassed, or when I have this capacitor here, we will not consider the effect of this resistance, because in effect there is a short across this, right? The reactance offered by the capacitance is very, very small. This is the first case. Now let me look at the second case where I have, let me use this color itself. I have again at 1 megahertz, I am taking the typical value of CGS capacitance. CGS is almost equal to 1 picofarad. It generally it will be in picofarad range. Sometimes it can be even femtofarad also. That again depends on the technology in which the MOSFET is fabricated, right? So can you tell me what is XC of GS here by considering the value of 1 megahertz and 1 picofarad? Can I get answers here in the chat box? All right, it is very close to 159,159. Yeah, so it is 159 point, yeah, 15 kilo, right? And I'm very sure that you will agree with me that this is actually a huge value, right? So whenever you have a large resistance, that can be equated to an open circuit. Why? Because large resistance will allow only less current or negligible current to flow through it, right? Or the reactance offered is 159 kilo, that can be assumed as large quantity, and this will result in actually, so what will be the effect of this capacitors? These capacitors are actually acting as open circuit because of the large reactance offered by it. All right. So these are some typical values what I have taken just to show that at mid frequency range. So mid frequency is not exactly 1 mega. It can be from lower kilohertz to a few megahertz range, right? So in general, we consider the capacitors, the coupling capacitors and bypass capacitors as short, as the reactance offered by them is very, very small. And the parasitic or structural capacitance we consider as open because the reactance offered by them is very, very large. That is why even in the gain expression we did not consider, because there is no effect from this bypass and structural capacitance. That is why there is no inclusion of those components in the mid frequency gain that resulted in a flat band here. There is no variation here because it is not depending on frequency, right? So as we discussed the effect of the capacitors in the mid frequency, let us see what happens at low frequency and what happens at high frequency, right? So with that, we'll come back and we'll conclude. So any doubts here? All right. So let me look at this low frequency effect. So low frequency. Let me first consider the effect of CC1, CC2, and CS. Right. So what will happen? We can say that XC is equal to 1 by 2 pi F into C. C can be CC1, CC2, or CC3. But what happens here is, as F is low, or as F reduces, since the denominator component F is reducing, XC is going to be very large, right? The reactance offered by these capacitors will be very large, and that will result in what? That will ultimately result in the capacitors will actually act as open because of the very large reactance offered by them. Now, coming back to the circuit diagram, what will happen if the capacitive reactance is very, very large at low frequency? So if the reactance is very, very large, then the signal will not be coupled to the input of the transistor. Signal will not be taken, or signal cannot be taken from the drain to the output, because these capacitors are here, and actually in fact it is acting a kind of blocking, right? Blocking in the sense, since the reactance offered is huge, the signal will not be efficiently coupled to the gate, or signal cannot be taken out from the drain. So that means as a signal itself is getting dropped, I can write here that this result in, therefore the signal will not be coupled properly. Signal will not be coupled properly. So what will be the result of that? If the signal is not coupled properly, definitely the gain also will drop, right? So this will result in a gain reduction. Therefore, gain reduces. So this is the effect what we are seeing here in the in the frequency response plot. At low frequency, since these coupling capacitors and bypass capacitors are offering a huge reactance, the signal is not effectively coupled. If the signal is not coming in, if the signal is not taken from here, gain will automatically gain will reduce. So here you can see this effect or this reduction here. So this we generally call as low frequency band. This is low frequency band, and here the effect is the gain is falling. So the gain falls due to, so who are the responsible components here? Gain falls here due to CC1, CC2 and CS, right? Because let me write the reason also here, because these are acting as open. All right, so coming back to low frequency, let us see the effect of CGS and CGD. So at low frequency, this is CGS and this is CGD. What will happen? Yeah, the effect is same. So let me write this for CGS and CGD: 1 by 2 pi f into CGS. As f reduces, this Xc increases, and this also will actually act as open. Right. Now, when your parasitic capacitance act as open, that is not going to affect you directly at low frequency, because what is the effect at low frequency? This is acting as open. That is why we did not consider actually parasitic capacitance in a regular analysis. If you remember, here also the structural capacitance are acting as open. At low frequency also the structural capacitors are acting as open. That means at low frequency or mid frequency, we never consider the CGS and CGD, and that is not going to bring any effect on your frequency response at the lower side. All right, I hope you are with me. Now let me look at this high frequency response. So we have looked at mid frequency, low frequency, and let me look at the high frequency. So what happens at high frequency? Again, at high frequency we have CC1, CC2 and CS. Now these will, so here both are acting as open. Now at high frequency, we know that Xc is again 1 by 2 pi f CC1. As f increases, your Xc, yeah, f is in the denominator. As this increases, what will happen? Xc will actually reduce, right? So Xc, if Xc is reducing, ultimately at very high frequency, we can say that these coupling capacitors will act as short. Right. Now, can we look back and say what will be the effect of this capacitors at high frequency? This is acting as short. When the coupling capacitors are acting as short, it is not going to affect the high frequency response, because the signal will be directly coupled, and signal will be coupled even from the output to the load. So there is no variation to the gain as such because of coupling capacitors at high frequency, because they are acting as short. Now let us look at the effect of the structural capacitors CGS and CGD. So again, this is equal to 1 by 2 pi f into either CGS or CGD. As f increases, this Xc actually reduces. If Xc reduces, as we mentioned before, it will act as a short. Now what is the effect? Now if CGS and CGD is acting as short, you can see that this will be replaced by a short, and this also will be replaced by a short. Right. So what happens when I say that the CGS capacitor is acting as a short? Effectively, the VGS voltage itself is actually reducing to 0. If your VGS voltage is reducing to 0, in fact, your output itself will be 0, because your MOSFET is responding to a VGS voltage, and now if your VGS voltage is acting as a short, then definitely your MOSFET output also will be 0 or less, or I can say gain will be reducing at high frequency. At the same time, you see, look at CGD. CGD is directly coupling from input to output. There also, if it is acting as a short, your output is almost same as input. Right, that will result in actually a reduction in gain from this current state. Or I can mark here, this is actually your high frequency band. This is high frequency band, and now here the gain reduction is happening, or the gain is falling here. Gain falls due to CGS and CGD, because they are actually acting as short. right? So at mid frequency, both capacitors are acting as open, both are open. So your CC1, CC2, sorry, CC1, CC2 are acting as short, and your CGS, CGD is acting as open, and you have no problem, or there is no as such there is no influence from the capacitors. But at low frequency, since the coupling capacitors are open, the signal is not effectively coupled, so gain falls. At high frequency, your parasitic capacitance or structural capacitors are acting as short, so as a result your gain falls. So this is how we understand the frequency response. And now since gain is falling at high frequency and low frequency, we consider, or we evaluate, or we consider only a set of frequencies where you have a decent gain as a mid frequency band, and that is expressed by the higher cutoff frequency and lower cutoff frequency, and we express those set of frequencies as bandwidth, where bandwidth is defined as the higher cutoff frequency minus lower cutoff frequency, fh minus fl. All right. I hope you understood what I have explained now. If there are questions, I can take it up now. Any questions?
Sir, could you explain how that gain falls at high frequency again?
Oh, at high frequency, yeah. So look at this. At high frequency, you have CGS and CGD capacitors. Now, say if your CGS is acting as short, right?
Yes, sir,
Because
yeah.
I stated that CGS will have a very low reactance. As a result, it is acting as a short. That means you effectively you have a zero VGS if it is short.
Yeah.
Right. Now, from the equivalent circuit of MOSFET, you know that the current which is flowing through the resistors here is in fact the GM-VGS current.
Yeah, yeah.
Right. Now, if your VGS is zero, the current source itself is actually zero.
Okay, so gain will be lesser than.
Yeah, it will be lesser. I can say the gain will be almost nil, and this will happen only at extremely high frequency. But the effect will be there starting from the high frequency itself.
Yes, sir, yes.
All right. Yeah.
Thank you, sir.
Yeah. Any other questions? Okay, if there are no questions, or if you have questions, you can think over and you can ask me at the end of the class. But now I'll ask you to draw so now I have a circuit diagram here, right? So we understood the frequency response. At low, this is a problem. At high, this is a problem. And mid frequency, we will get a decent gain. Now let us analyze the circuit. Let me take the circuit, draw the equivalent circuit, and look at the let us evaluate the cutoff frequency like FL, FH. How will you evaluate this FL? How will you evaluate this FH? What is the relation of this FL with respect to the capacitors, the coupling capacitors? What is the effect of FH with respect to the bypass capacitor? So all those analysis we'll do now. So can you draw the equivalent circuit for this circuit diagram given, the CS amplifier? Then I have to introduce one more concept, and then later we'll go for the analysis. So I have drawn an equivalent a circuit diagram there, CS amplifier. What I'm asking is to draw the equivalent circuit, a small signal equivalent circuit, but at high frequency. Madhusudan?
Yes, sir.
Yeah, Madhusudan, can you help me in drawing the equivalent circuit of the CS amplifier?
Sir, I'll don't know. I was absent for previous class.
Oh, all right. Okay. Okay, but still you can no high frequency. Forget about high frequency, but just help me to draw the equivalent circuit of CS amplifier.
Sir, R pi resistor.
This is MOSFET.
Oh, sorry, sir.
Yeah.
So we can draw open like circuit in VGS.
VGS. Okay. Very good. Yes.
And then dependent source.
All right. What is the dependent source here?
So GM VGS.
GM into VGS. Okay. Now, what I'm asking is with respect to the circuit diagram I'm showing here. Okay. With respect to this. Yes. Go ahead. Next.
Sir, RS we can draw at source.
RS. Okay. Where should I draw RS?
The source at source.
Okay. Okay. Will there be RS there?
So with the capacitor it can be nullified.
Yes, because at high frequency, even the capacitor CS is acting as a short, right? That is what just now we discussed. So RS will not be there. So let me first complete the equivalent circuit of MOSFET. This is the equivalent circuit of MOSFET with R naught.
Not yes.
Yeah. Now I have to come. Yeah, that's
RD
okay.
and
Yeah.
RL.
RD and RL. Very good. Yes. So this should be grounded. This is RD. And this is RL. And this is your output V out.
And R1 parallel R2.
Yeah, all right. Thank you, Madhusudan. Yeah, I understood that you know the sequence. Only thing is we have to add the high frequency capacitors, right? Yeah, so this is R1 parallel to R2. Now, there is a small difference in this circuit because I have included a signal resistance also. Now the CC1 is acting as a short, so from that point, I have to add the signal resistance, which is R signal, and that will end up here with the V signal. Right. I hope we included everything from the circuit, RD, RL, everything. Yeah. Now, since it is high frequency, right? So these capacitors are actually acting as short, but acting as short, and it is not affecting the circuit. But the other capacitors, CGS and CGD, which is acting as short, and it is affecting the gain of the circuit. So I am actually including those capacitors here to study how it is just to include those values in the gain expression, right? So this is CGD and this is CGS. This is how I included the high frequency capacitors. All right, I think this equivalent circuit is clear. Just I have brought in the high frequency equivalent circuit and I included CGD and CGS. The reason is CGS and CGD are actually affecting the circuit at high frequency by there is a drop in the gain. But what about CC1, CC2 and CS? It is not affecting the gain. That is why we are not considering it. Now, now we are going to learn something new. You can see in this equivalent circuit that till now, for all the equivalent circuit and the analysis what we have done, we did not have any capacitors actually acting in between, which is having a connection or which is giving a path from input to output. Can you observe that? So by including the capacitors here, the high frequency equivalent circuit capacitors here, I can say that there is an interaction between the input side and the output side through this capacitor, or capacitor is actually providing an additional path of interaction from input to output. In the absence of capacitor, how it was, whatever voltage is coming here, your MOSFET is actually acting as a current source, a controlled current source, and producing the current GMVGS. But now, between input and output, through this capacitor, there is an interaction happening. Right. Now, whenever you have an element sitting, whenever you have an element or an impedance sitting in between the input and output as an additional path. Now, this is not the single path here. Even we know that without the presence of these capacitors, the output and input are related through this GM-VGS component. So this is considered as a main signal path. So this is considered as the main signal path from here to here. 1 second. So this is considered as the main signal path. Right, this is the main signal path, but now we have this as the additional path of interaction. Right, so whenever you have an element sitting between input and output as an additional path, now we have to understand how to solve or how to approach such circuits. So right, so for that to understand or to analyze such circuits, we use a theorem, and that theorem is called as Miller's theorem. Have you come across this theorem in your network analysis class? Can I get the answer in chat box? Chat box, any answers? No, all right, yeah. Probably you would have learned about Millman's theorem, but not Miller's theorem, right? So let me explain what is Miller's theorem. So after understanding about Miller's theorem, we'll go back and we'll analyze this circuit, right? So so to understand in a simple way, I am actually taking a small block here. Say this is a block. Say, for example, this is an amplifier block which is giving a gain of A. Right. Now, the input to this amplifier is plus minus V1. I'm calling it as V1. It can be Vin also. Now, output from this amplifier is considered as V2. Right. And as I told before, through this amplifier, or this is the main signal path. So the input and output interaction is through this amplifier box. Right. In that case, I can write that V2 is equal to A into V1, as V2 is acting as the output and V1 is acting as the input terminal. So V2 is equal to A into V1. Now, to understand or to study what is there in our equivalent circuit, we have an additional element which is sitting in between input and output, right? So in this box, I am actually including that from input to output, there is some impedance sitting, and I am calling this as Z. So main signal path is shown in pink, and the additional interaction is through this impedance path of Z. Right. Now, what I want here is, since this impedance is not grounded, or since the impedance is connected between input and output, I want to get the equivalent of this impedance so that I can break this impedance into input side and output side. Right. That is the Miller's theorem is actually used for that, or Miller's theorem explains how you can get an equivalent of this impedance which is sitting in the feed through path, and how I can obtain the equivalent of this impedance to the input side as well as the output side. So let me explain this first. It may take a bit of time for you to understand. So what I'm doing here is, Miller's theorem states that if you have a path in addition to the main signal path, where if you have an impedance, that circuit can be decomposed into in this fashion. How it is you can break the impedance sitting in the feedback path as Z1 on the input side and Z2 on the output side. This is Z2, where this is V1. Now the current flowing through this is, say this is I. Now the current flowing through this is I, and the current, the same current is actually, so the current through the impedance is not changed. So the current flowing from V1 to impedance Z1 to ground, then from here to Z2, and then to the output. So this is actually the V2 terminal, right? All right. So Miller's theorem states that if you have an impedance, if you have a path which is having an impedance apart from main signal path, that can be decomposed into two equivalent impedances, Z1 on input side and Z2 on the output side. Now we should understand what is the relation between this Z1 and this Z and this Z2 and this Z, right? So to understand that, I'm just using certain equations here. So let me write the current in the main circuit. What is the current in the main circuit? I can write V1 minus V2. So this is V1 and this is V2. So V1 minus V2 divided by Z is actually the current I. I hope you are following this. So the current I through this additional path is actually V1 minus V2 by Z, right? Now the same current is actually flowing through Z1 also. So what is that current? V1 minus 0 by Z1 is actually I. So I can write here as V1 minus 0 by Z1. Through this, I got a relation between Z and Z1. What is the relation? I can write that Z1 is equal to, what is Z1? Z into V1 divided by V1 minus V2, or this can be further written as Z into 1 by 1 minus V2 by V1, or I can write this as Z is equal to, what is V2 by V1? V2 by V1 is actually A. So Z can be Z1 can be written as Z divided by 1 minus A. Are you with me? So if you have an impedance in the feedback path, so you can break or you can draw the equivalent of that impedance at the input side as Z1, and to get the value of the new impedance, you can get it from the formula of Z by 1 minus A, where A is the gain in the main signal path. So I'll apply the same thing to the circuit, some circuits to get more clarity. So this is how we obtain the value of Z1. Now, how to get the value of Z2? Z2 is also same, right? V1 minus V2 by Z is actually this current. Now, how is that current flowing through Z2? That current is equal to 0 minus V2 by Z2, right? So if I rearrange this, I can, if I take the reciprocal, Z by V1 minus V2 is equal to Z2 minus Z2 divided by V2, or if I write this, I can write Z2 as minus of Z into V2 by V1 minus V2, or I can further write this as, okay, if I take minus inside, I can write this as, and say I'm dividing, I'm taking minus V2 and I'm dividing in the denominator, so I can write this as V2, okay, let me go to the next page. I can write Z2 is equal to minus Z into V2 by V1 minus V2, which is equal to Z divided by V2 by V2 minus V1 by V2, or I can write Z2 as Z by 1 minus 1 by A, right? So whenever you have an impedance in the additional path that is giving an interaction between input and output, that can be broken, that can be decomposed into two impedances. One Z1 whose value is Z by 1 minus A, and the other one Z2 whose value is Z by 1 minus 1 by A, right? So this is what Miller's theorem is giving you to how to solve circuits whenever you have an additional impedance sitting in between input and output. Not an additional impedance, additional path apart from the main signal path. Now in the next class, we'll apply this Miller's theorem to this circuit, and we'll solve and see how we can include these things into the in the gain, as well as we also will see what is the relationship between the cutoff frequency and the capacitors, right? So thank you so much for joining today's class. I hope this is clear. If you have doubts, I'll open now for discussion.